So the name of this unit is Momentum and Impulse. So to start us off, I want to point from the very beginning that momentum is an extension of inertia. So from the very beginning, I want you to understand that this is a measurement that has to do with an object's resistance to changes in motion. And the word inertia is how difficult it is. What's that? I think you dropped something. I dropped money. I don't want to do that. Okay, so we're talking about momentum and impulse. So I want to start by saying momentum is a measure of an object's inertia. In fact, I would say that from the very beginning of this conversation that you need to be reminded about what inertia is. So when we measured inertia earlier in the year, we measured it by measuring an object's mass. We said that an object's inertial mass, or just its mass, is how difficult it is to change the object's motion. So I used a lot of different ways of describing that. I said it was how difficult it was to change its motion, an object's resistance to acceleration. We used the concept of inertia directly in line with Newton's second law. We said that if you apply an unbalanced force, how much it accelerates will depend on the object's inertia. Bigger objects are harder to move. Littler objects are easier to move. It's a pretty straightforward idea, pretty straightforward concept. Here, we're going to change it a little bit. Momentum is an object's inertia while moving, or inertia due to motion. What we didn't talk about first semester that we really need to kind of bring up now is that when an object is moving, its inertia changes. The faster an object moves, the more difficult it is to change that object's motion. Momentum is a measure of that property. It's a measure of an object's inertia while moving. So we use a lowercase p as the symbol for momentum because that makes perfect sense, I'm sure. And momentum is a vector, so it has direction. And it is the fact that it has direction that is directly applicable to all conversations about momentum. I'm going to say this kind of subtly, and in your notes, you should probably put a huge banner ad. The thing that you will likely get wrong the most about momentum is you'll forget that momentum has direction. So if you want to ensure that you don't screw up the simple trick questions, you have to start remembering that the direction of momentum matters. It is a vector quantity. Momentum is merely the product of mass and velocity, and momentum takes its direction from the velocity. So whatever the direction the velocity is, that's the direction of the momentum. The unit for momentum is nothing special. It's just kilogram meter per second. We don't have any special name for it. So when we deal with momentum, you don't have to convert it to newtons or something like that, but be aware it's a complex unit. It has all three of those in it. So this is the stuff that's, in the textbook that you need to know. None of this is particularly important. However, I do want you to understand that momentum was the most important concept according to Newton. We teach physics completely different than the way he envisioned the formulation of physics. He started with momentum and built all the properties from momentum, as opposed to the way we do it, where we started with motion, not even caring how big the object was. He started with momentum. In fact, his original version of Newton's second law wasn't about mass and acceleration. It was about the rate of change of momentum. This is really Newton's second law. So we're going to start here a little bit because I want to begin really by talking about impulse. Now that I've defined what momentum is, impulse is really the focus for the rest of the class today. And so to understand impulse, we're going to take Newton's second law. We're just going to do a little bit of work to it. We're going to multiply both sides by delta t. And we're going to start from here, because this is known as impulse. Impulse is a value, it's a relationship that talks about how you change something's momentum. Impulse has two parts to it. If we look clearly, there's the left side and the right side of the impulse relationship. The right side is just a delta, and I don't know if you guys remember what a delta is, but I want to make sure I drive this home. Delta is final minus initial. It's change in momentum. So the right side of this is the change in momentum. The left side of this is force applied for a time. We tend to say that this side is the cause of an impulse, and this side is the result of an impulse, or the effect. Both sides of this represent impulse, meaning you can calculate impulse by either talking about force and time or by talking about change in momentum. They both refer to the same quantity. So if you're asked to calculate impulse, look carefully at the information they provide you. There's going to be enough information for you to figure out one side or the other. But the concept of impulse is relatively simple. If you wish to change something's momentum, you have to apply a force for a given time interval. This isn't much different than work. Do you guys remember way back we talked about work? If we compare this to work, work was force times distance. I'm leaving the net force out for just a minute. This was our basic definition of work. And we said that any force could do work. But then we augmented that and said if the work is done by a net force, then it would cause a change in kinetic energy. We had this discussion way back first semester November. So there's clearly a similarity here between work and impulse. But be careful. Applying an impulse doesn't necessarily mean you do work, and doing work doesn't always result in an impulse. These are separate things. In order for work to be done, the force has to be applied over a change in position. For impulse, it's about time. So if you just bounce a ball, you're probably not doing any work on the ball. The floor didn't move anywhere. So during the time in which the ball is connecting with the floor and the floor is applying a force, it's not like the floor moved any distance during that time interval. There's no work done on the ball, but an impulse is applied to the ball. So you can have an impulse without having work done. We'll be very clear about that. These are not the same measurement, and they talk about different things. Impulse is a vector. It's not clear that that's true, but make it clear in your notes. Impulse is a vector. More importantly, the direction of impulse isn't necessarily the direction of the momentum. The direction of an impulse is the direction of the change in momentum. Most importantly, if you're taking notes and you want to be very accurate, the direction of an impulse is in the direction of the unbalanced force. That's the direction of an impulse. It's in the direction of the unbalanced force. let's take a moment and do a simple impulse calculation. You're going to want your phone for this. So if you have your phone, please take it out. Not your phone. You'll need a calculator for this. Sorry. All right. So we throw a ball and it bounces off a hard surface and bounces away from that surface. So we throw the ball at 5 meters per second, strikes the surface, bounces off, comes back at us at 4 meters per second. If I was to ask you to calculate the impulse that was applied to the ball, then you would have enough information to deal with the effect side. I know that because I gave things like mass and I gave things like velocity. Those are clues that the impulse is calculated by calculating the effect. If I gave things like force and time, then I'd be talking about the causal side of impulse. So be careful. They're going to mix those things up and they're going to make it more convoluted than this. I'm starting with something very simple. Now, to actually calculate the impulse, a couple of reminders. First, change in momentum is final minus initial. So we're looking at mv final minus mv initial. Careful to remind myself that the mass doesn't change here, but the velocity has a clear change. Now, if this is not our first time talking about this, I would try to see if I could trick you. But I don't want to trick you on this one. This is our first time looking at this. So just a big heads up. Momentum is a vector quantity. Therefore, I see a one-dimensional problem. So I need to assign direction. And it doesn't matter what direction I assign to be positive, just need to be consistent. So let's say I decide that in this problem, this direction will be positive. That's going to mean that my calculation for impulse, I have to make the 4 negative, because when it bounces off the wall, it's now traveling in the negative direction. I do my work here, and I'm going to get negative 18 kilograms meters per second. This was the impulse experienced by the ball due to its contact with the wall. It's pretty straightforward and pretty simple, but there generally are follow-up questions. Like, if the ball was in contact with the surface for 0.4 seconds, how much force did it experience? It's a pretty straightforward follow-up question. And if you're seeing where I'm going with this, we have found the impulse on the ball. We could talk about how much force must have been applied to the ball due to its contact with the wall. If I give you the time of contact, then you should be able to figure out how much force was applied to the ball and the direction of that force. Now, I don't really care about plugging in numbers. I'm trying to give you a feel for what these problems are going to be about. Now, this one's not too terrible, but almost every problem involving impulse or momentum is going to try and provide reflections of energy at the same time. Did this ball lose any energy? Now, you should be able to answer that with no difficulty by just observing the before case and the after case. Energy doesn't have direction. And when I look at how fast the ball was going before, and I look at how fast the ball was going after, I'm seeing that the ball is clearly traveling slower. Energy is about velocity too. So does the ball have less energy or more energy after it bounces off the wall? It's got to be less. The velocity is a little bit smaller, but energy is really, really tied to velocity. So a change of velocity means big changes for energy. Let's try one more, but this time I'm going to purposely try to trick you, okay? And I'm going to see things you're supposed to already remember. Bless you. All right, so I drop a ball. It strikes the ground, bounces back up. Okay, so this is my first position, second position, third position. Everybody imagine this so far? So, did this ball lose energy due to its contact with the ground? How can you tell? It didn't bounce as high, right? It has less gravitational potential energy after it bounced than before. Remember, with energy, we can use conservation of energy, and we can also compare states of energy. Since the ball didn't make it back to its original height, I can only assume that it lost some energy when it was hitting the ground. It probably made noise, generated a little heat, stuff like that. So here's what I'd like you to tell me, and this one's a hard question, but you guys are smart people. Can you figure out what the impulse experienced by the ball was? I'll give you a hint. Impulse is all about velocity. So you're going to have to figure out velocity here. So I'll say it again. Can you figure out the impulse experienced by the ball? All right. So I'm hoping you guys had a chance to take a look at this. Did you need the hint? Or did you figure out that you could use energy? You could even use motion equations if you wanted. But you needed a method to figure out how fast the ball was going when it reached the ground. And then, of course, using how high it bounced back up, you needed a method to figure out how fast it was going when it left the ground. Energy is probably the best way to do that, which would have been mgh equals 1/2 mv squared as it falls. So v equals the square root of 2gh, or square root of 2 times 10 times 2. So how fast was it going when it reached the ground? 6.3? All right. Meters per second. Sounds good to me. When you took the square root, it's plus or minus. And that's important because energy can't tell you direction. What direction was the ball moving just before it struck the ground? Down. So is downwards going to be positive or is downwards going to be negative? So a decision has to be made so that you can be consistent. So if we're saying downwards is negative, then the actual velocity just before it struck the ground was negative 6.3. Since we're going to be using this in a momentum calculation, we have to make sure that we're careful to consider direction. On the other side, we have mgh equals 1/2 mv squared. So V equals square root of 2GH, or V equals the square root of 2 times 10 times 1.75. How fast did the ball recoil? Yes, sir? Should I make that positive or should I make that negative? Positive. It recoiled upwards. We've said that downwards is negative, so upwards is positive. That doesn't answer the question. This just helps us figure out the velocity just before it strikes the ground and the velocity just after it strikes the ground. To answer the question now, we have to do a change in momentum problem. Not hard, but there has to be some understanding that these problems are clearly going to mix energy and momentum. It's not terrible, but it starts giving us a bigger picture of what's happening in nature. So again, 2 times 5.9 minus 2 times negative 6.3. And I will point out, the calculations aren't terrible, but when we have problems that have calculations like this, the mistakes tend to be made in some of the places where you tend to not think about them. Direction, negative signs, positive signs. That tends to be the nature of the problem. Your answer is positive, which means the impulse was upwards. That's not a mistake. The force on the ball was upwards the whole time, so the impulse had to also be upwards. All right, so this is the basics of how impulse questions are going to be asked. And of course, follow-up questions like if the ball was in contact with the ground for a couple of milliseconds, what was the force on the ball? There can be follow-up like that. Not particularly interested in seeing if I can be tedious and find every little wrinkle here. I want you to understand that impulse is a measure of the change in momentum of an object. Now, if you were lucky enough to be in my room a few minutes ago, before the bell rang, then you know that I dropped one of my favorite coffee mugs in the back of the room. And I'll get over it. It's just a coffee mug, but I am sad. It was my villain's coffee mug. No. And I was feeling particularly villainous this morning. I was going to drink out of my villain's coffee mug, and now it's in pieces in my trash can. And oh, probably not. And when we consider that I dropped the coffee mug above the tile floor, the mug fell, whatever distance this was, hit the ground, and was brought to rest by the action of the ground. So the cup experienced an impulse. The final momentum of the pieces was 0, but it clearly had a momentum right as it struck the ground. And it got that momentum because it was accelerated downwards by gravity. So there's the moment then just before it strikes the ground. And then pieces everywhere, nothing but gore and sad, broken, failed dreams. We're in physics. It fits. If only my room had been carpeted, right? If they had just carpeted the room. It's possible that if my room was carpeted, instead of being left with nothing but, gore and carnage, maybe if it was carpeted, and I had dropped my coffee mug, the mug could have survived, soft landed and survived. That's plausible, isn't it? Have you ever dropped something on the carpet and it didn't break? But maybe if you dropped it on the tile floor, it would have broken? This has been my experience. I think phone is an excellent example. Drop your phone on carpet, probably not going to shatter the screen. Drop phone on tile, probably going to shatter the screen. Now, I'm not trying to trick you here, but which cup experienced the greater impulse? The cup over the tile or the cup over the carpet? Why do you say it's neither?
Because it's the same portion of
That explanation isn't sufficient, but it's not necessarily wrong. Somebody have a better explanation? All right, I am actively trying to trick you. Yes, sir?
I think that despite the material of the floor, I think that whatever force it is and how fast it's going down, it's still going to have the same effect, just with what material it is. It'll either break or stay still.
Remember, I'm asking about impulse. Would you agree that in both cases I've been careful to draw the circumstances upon which the cup was dropped so that they look like they were dropped from the same height?
Mm-hmm.
So is it likely they were traveling the same velocity when they reached the ground?
Yes.
Did both cups come to rest? Yes. They both experienced the same change in momentum. They went from the same velocity to zero. So both cups experienced the same impulse.
Yes.
Because they're both stopped. Now, the problem is the cup that hit the carpet must have taken longer to stop than the cup that struck the tile. Remember, they both have the same impulse. So the right side of this formula is the same. It's not impulse that breaks the cup, it's force that breaks the cup. This side being the same, all I can manipulate over here is time. I can make it take longer to stop or shorter to stop. If I make it take longer to stop, well, that's an inverse relationship. If the time can become a bigger number, then the force can become a smaller number. How many of you have been fortunate or unfortunate enough to have to do one of those egg tosses at like a picnic? Maybe a water balloon toss? Only a couple of you? Come on, at some point you probably reached the age where you were no longer asked to do it. You know what I'm talking about? Mm-hmm. And you were thankful of that. But there was also that awkward transitional time when you were probably old enough not to do it anymore, but they didn't have enough people, so you're the oldest kid out there throwing to some little kid. Mm-hmm. Probably your desire to want to just peg that kid with the egg was probably pretty high. And there's probably some stupid award if you got far enough apart. The idea is you throw the egg at the other kid catches it, and now for torture purposes, we all take a step backwards and try it again. Right? An egg toss or a water balloon toss. Did you notice how you tried to catch the egg or the water balloon? You didn't just put your hands out there and let it splat you.
That's exactly what I would have.
Yeah. You did one of those, right?
If you could.
If you could, if you were capable. In that case, of course, you're still going to stop the egg or the water balloon. Your choice is whether it ruptures when it hits you or not. You are manipulating the time. If you don't like that one, in a car accident, everybody in the car accident is going to be brought to rest. If you are a passenger in the car, you have options on how you can be brought to rest, right? There's the dashboard. The pillowy softness of the dashboard can bring you to rest. There's the incredible flexibility and give of the seatbelt. It can bring you to rest. There's the pillowy softness of the airbag as it explodes in front of you. It can bring you to rest. The windshield is less likely to bring you to rest, but can. It's nice and soft. Of course, when we consider all of those, I hope you realize it doesn't really matter which one of these we choose to discuss. You're going to be brought to rest. The truth is, if I want to manipulate the force on you, then what I'm manipulating is how long it takes to bring you to rest. Each one of these different restraint systems is an attempt to change how long it takes for you to come to rest. The dashboard, not going to take very long to bring you to rest. Seatbelt, about 10 times longer than the dashboard. So if the dashboard brings you to rest in milliseconds, the seatbelt brings you to rest in tens of milliseconds. Now think about what that means. 10 times longer to stop is 10 times less force. An airbag brings you to rest in hundreds of milliseconds. That's 100 times less force than a dashboard. Now, the least amount of force would be for you to be ejected from the car and let friction bring you to rest. But that's not ideal either, clearly. Being a streak on the sidewalk or the street, not an ideal circumstance. In all cases, we're still just looking at manipulating these.